All right, we are on the last section. It's a bit of a long section. Components of a vector and unit vectors. Some of these concepts may seem difficult to begin with, but I think you'll catch on. Let's start with components of a vector. We have here a vector A, and if we look at it just as a triangle, we can see that AY is vertical. It's at the end of the vector A, and AX is horizontal and it's along the x-axis. That's one way to represent it. It's easier to see there that the cosine theta, the sine theta is equal to AY over A. And you can also see here that the, sine theta is AY over A, and cosine theta is AX over A. But this is also one of the ways that we represent components of a vector along the axes. So you see vector A there, and AX lies along the x-axis, and AY lies along the y-axis. But still, the cosine of theta is still AX over A, and the sine of theta is still AY over A, because even though we define it as the sign opposite, it is still, you remember how I said that vectors, you can move them around. The fact that it's at the end of the triangle, it's the same vector. So those two vectors, the AY, in either case is the same vector, irrespective of whether it's at the end of the triangle or on the axes. So cosine theta equals AX over A. From that, we get that AX is equal to A cosine theta, and sine theta is equal to AY over A. And from that, we can derive that AY is equal to A sine theta. And the magnitude of A, the magnitude of vector A, is the square root of the sum of the square of its components, AX squared plus AY squared. And the angle theta is determined by the tangent inverse, or arctan. Some people say arctangent, or tangent inverse, tangent to the -1, of the vertical component over the horizontal component, the AY over AX. But don't just, you need to know what quadrant you're in. Don't just take what your calculator says. Unless your calculator is able to look at the individual components and their positive or negative values, you're going to get a vector between, you're going to get an angle between -90 and 90. So you have to be careful when using a calculator. You have to know what quadrant you're in, and it's good to know, it's good to do a sketch so you can look and say, is that reasonable? Does it look like 30 degrees, or does it look like 210 degrees? You know, so and we'll get more practice on that when we do the vector table. Okay, and here's exactly what I'm talking about. If both AX and AY are positive, then you're in the first quadrant. That upper right-hand quadrant is the first quadrant. There your result will be between 0 and 90 degrees. Now, if you have AX is negative, but AY is positive, then your answer is going to be between 90 and 180 degrees, or should be between 90 and 180 degrees. Be careful of that. Now, if they're both negative, and you take something like the tangent, you're going to get a positive angle. You're going to get an angle between 0 and 90, but it's not going to be. It's going to be between, your answer really should be between 180 and 270 degrees. Be careful of that. And then if your X is positive and your Y is negative, then your result should be between 270 and 360 degrees. Of course, if you go all the way to 360 degrees, that's zero. There's no reason to write 360. That's 0 degrees. So be aware of your quadrants. We used to. When I was in high school, I went to Central Catholic. That was way back when. That was. Let me get. Oops, not that one. All notes. Let's. Where I should have had. No, I may just make one if I'm. Yeah, here we go. So let me stop this share, and this may help you. It may not. It may not help. But let's share the iPad. And where's my pen? Oh man, I still have it in my briefcase. Here it is. So and right now we have what is called VIA, but back when I was in high school, we had the we had the we had come on, let's put let's make it straight. We had the San Antonio Transit Company. Now, how does that help us? Well, this was to help us know which of the functions were positive. So, if you look at that San Antonio Transit Company, and there may be other mnemonics, but this is the one I learned. Sorry that now it's called VIA, but way back then it was called San Antonio Transit Company. And in this one, all the functions, sine, cosine, tangent, are all positive. All of them are positive. In the second quadrant, the sine is positive. The sine is positive, so that means the cosine and tangent are negative. Why? Because the x is negative. The x is in this direction. In here, you have both x and y are both positive. Here, only the y is positive and the x is negative. So sine all, what do you think the t stands for? Well, the tangent. The tangent, well, you have the y is negative and the x is negative, but when you have a negative y over a negative x, you're going to get a positive. So the tangent, tangent of theta equals y over x. So the tangent ends up being positive. Guess what? The cosine is negative because the x is negative, and the cosine is negative, and the sine are negative because of the negative x and negative y. And here, the cosine is positive. Why? Because the x is positive, but the y is negative. So San Antonio Transit Company, sine, all, tangent, cosine. Hopefully that helps. If not, just forget it, and maybe that you've learned another mnemonic, and use that one. But hopefully this helps. Okay, let's go back to the PowerPoint, and let's take a little quiz. Choose the correct response to make the sentence true. A component of a vector is always, never, sometimes, or it's either always, never, or sometimes larger than the magnitude of the vector. Well, if it is in the it can't always be larger because the the magnitude of the vector is the hypotenuse. And the hypotenuse on a regular right triangle is always larger than either of the components. Is it never larger? Well, in the case where you have 0-degree angle, that you can't use that never. And oh, wait a minute. The question is, a component of a vector is never larger, and that's the key. I missed that. I almost led you astray. It is never larger than the magnitude of the vector. And is it sometimes larger? No. If it's at the most it can be equal. So the answer here is never. It's never larger. It's never larger than the magnitude. It can be equal to the magnitude, but never larger. Okay, let's. Now we're going to get to unit vectors, and I think I'm going to break this. Well, no, we'll just keep going. I, J, and K. When it's a little I hat, J hat, K hat. Whenever you see the hat, it's this means that the magnitude of this vector is 1, but the I represents the x, a unit vector in the x direction. The J is a unit vector in the y direction, and the K is a unit vector in the z direction. Now, there's going to be different books represent this different ways, but this is the one that this book uses, the IJK, and we'll try to stick with that convention. These are all it is trying to give you a direction. If it's I, it's the X. If it's J, it's the Y. If it's K, it's the Z. So on a regular Cartesian coordinate, you have vector A. The components are AX in the I direction and AY in the J direction. Now, so A is equal to AXI plus AYJ. Now, it doesn't have to be X and Y. It could be radius and the theta. But again, they're unit vectors. That means their value is equal to 1. So R is R hat is a unit vector. On the coordinate system that you're using, there is a 1. So R is the unit vector radius. So you'll have the magnitude R might be 5. So 5 R hat would be 5 in that direction. Now theta is just a degree. I'm not going to use this much. I don't see much point in using it, but we will use the IJK. Okay. Vector addition using components. R is equal to A plus B, and we're going to do this in the vector table experiment. I'm not sure whether we're doing the vector table this Thursday or the following Thursday, but R equals A plus B. That means A is equal to AX I hat plus AY J hat plus BX I hat plus BY J hat. Well, how do we add these together? Well, we add the I components and we add the J components. We gather together the AX and BX. So R becomes AX plus BX times I hat, and we gather the Y components, AY plus BY times J hat. So that you whenever you have adding by components, you take all the X values and you take all the Y values, and if it's a three-dimensional, then you take all the K values. Okay, so R is equal to RX I hat plus RY J hat. Well, what is RX? RX is the AX plus BX, the one that you saw right above, inside the parentheses by the I hat. And what is RY? RY is equal to AY plus BY. The AY is in the AY plus BY is in the parentheses next to the J hat. Okay. Now, this is how it looks graphically. You can see that the AY and the AX are along the axes, and the BY and the BX are added to each one of those individually. So we see that the Rx is the sum, indeed, of AX plus BX, and we can see that RY is the sum of AY plus BY, and that gives us our resultant R. Okay, the magnitude of a vector. The R is equal to Rx squared plus Ry squared, which is equal to the sum of the X components, A plus BX, AX plus BX, quantity squared, plus the sum of the Y components squared. So it's AY plus BY, quantity squared. And the tangent of theta is equal to Ry divided by Rx. Well, that's the sum. Ry is equal to the sum of AY plus BY, and divided by the Rx, which is the sum of AX plus BX. Okay, vectors in 3 dimensions. All you do is you're going to gather to get the X components. You just add the AX and the BX. To get the Y components, you get, or the J components, J hat components, you get the AY plus BY, and the K hat components, you get the AZ plus BZ. And that's exactly what they've done here. You'll see inside the parentheses, the subscripts of I hat are both X, the subscripts of J hat are both Y, and the subscripts of K hat are both Z. So you gather the like components together. RZ is equal to AZ plus BZ, and R is equal to all 3 of them, the square root of all 3 of them squared, Rx squared plus Ry squared plus Rz squared. And so cosine theta in the X direction is equal to Rx over R. Cosine theta in the Y direction is Ry over R, and cosine theta in the Z direction is Rz over R. Okay, for which of the following vectors is the magnitude of the vector equal to one of the components of the vector? Well, the magnitude of the vector A was the square root of 16 plus, no, not 16, 4 plus 25. So it's the square root of 29. Well, that's bigger. The square root of 29 is bigger than both of those components. Now, what is the magnitude of B? Well, the magnitude of B is the square root of minus 3 squared, which is the square root of 9. Well, that's the magnitude of B is 3. Not minus 3, it's 3. So is minus 3 equal to 3? No. So the magnitude of the vector is not equal to the component. Now, the magnitude of C is the square root of 5 squared, which is the square root of 25, which is equal to 5. So yes, indeed, in that case, the magnitude of the vector is equal to the component of the vector. So the answer in this case is C. And boy, you can barely tell, but it is bolded to show that C is the correct answer. And that's the end of the chapter. So you're certainly welcome to contact me if you have any questions. We will be doing a lab hopefully soon, hopefully this week. I have to check with Dr. Wuku to see what his group is doing. We don't want the same thing that happened last week where we're short on equipment. All right.